In this video, we're going to talk about energy again. We'll talk briefly about the forms and the resources again. We'll go over the energy principle again, and we will also cover inclined planes again because we have a problem here with an inclined plane, and we're going to take a look at it. And we know that inclined planes are simple machines that allow us to do a lot of different things. So, for example, when you're moving with a U-Haul, or when you are driving up a hill, could be viewed as an inclined plane to get to a higher height, right? And so with energy, remember that energy is basically the ability to cause change, and it can be transferred or transformed. It's a property. We can measure it. It has units, and we know that the energy and mass of an object are very fluid. We can convert matter to energy and vice versa. We know that there's two basic types of energy. The potential energy is due to position or state, whereas kinetic energy is more due to the motion. And we know that energy can take on various different forms. A lot of times we're just looking at mechanical energy, and then we're splitting that into kinetic and potential, and then we're looking at gravitational or elastic. But we also look at non-mechanical forms of energy as well. So sound, thermal energy, electrical energy, magnetic energy, radiant energy, chemical energy, and nuclear energy are just a few ways that we can classify energy in terms of different forms. And so we end up getting to energy resources. So in society, we need energy, right? And so we get those from different sources, different resources. We need to convert energy to more useful types. And so we use biomass, hydropower, geothermal, wind, or solar energy that can be viewed as renewable. It can be replaced in a short period of time, versus non-renewable is a resource. There are resources that it takes a long time to replace them. And so both of them are used today, though, in society as part of producing useful forms of energy, electricity being one of the main ones that's useful to us. And conserving energy resources, therefore, is going to be important, especially moving forward into the future, where our energy demands aren't going down, really. So we need to make sure we understand on an individual level how we can reduce our use and rethink what we need. Instead of just buying things that we want. And then we also can think about how to reuse and repair things, and then recycle. And if we need to dispose of it, make sure you dispose of things properly. And so the energy principle basically is saying, hey, we can't create or destroy energy. And we have this universe. We have the energy within that universe constant, right? And we have a system and surroundings that we can define within the universe. And we're asking ourselves, hey, is the energy of the system constant? If it is, it's an isolated system. It's not interacting with the surroundings. But we know that a lot of times there is going to be energy flowing into and out of the system. And so we account for that with two mechanisms, one of which is work. And we define it such that any positive work is adding energy to the system. And we know that we can find work with force. And so forces can do work acting over certain distances. And so we basically take the force, multiply it by the displacement times the cosine of the angle in between. If it's not a constant force, we have to integrate. We end up also looking at the work kinetic energy theorem, which is a way of looking at work in terms of energy instead of forces and distances. And so we can derive it three different ways, with Newton's second law, with the kinematic equation, and with internal and surrounding work. We basically get to this idea that the network, not just any work, but the network is going to be equal to the change in kinetic energy. And so the other thing to consider is heat. So that's the other mechanism that can change energy in your system. We have a positive heat is going to add energy to your system. That's the way that it is defined. It's a system-centered definition. And so positive values are going to be adding energy to the system. Negative values are going to be subtracting energy from the system. And so it's just a way that we can account for heat and work. And we can also define heat as basically the flow of thermal energy. And we can say, okay, well, if we have a mass with some sort of a specific heat capacity and it undergoes a change in temperature, there must have been some heat associated with that. And we could also have heat associated with phase changes as well. Now, when we account for both of those things, work and heat, we pretty much get the first law of thermodynamics, which is our energy principle, basically saying that if we have any changes in energy of our system, it's going to be caused from heat or work. And we also know that even with a perfect machine, so like a Carnot engine, a lot of times we're not getting the work out that we put in. So with a Carnot engine, it's not 100% efficient because it can't perfectly convert all of the heat to work. And so you're going to always have some loss there. But with simple machines and things like that, it's useful to think about the work in is equal to the work out, and setting those equal to each other is nice. And the other thing to think about is a lot of times we're not considering heat, so we're just looking at work done. And so when that's the case, we can just say if there's any changes in energy of the system, which would be a change in kinetic or potential, it's due to the work from the surroundings on the system. Alrighty, so with an inclined plane, since we have an inclined plane in today's problem, remember there's an angle to that inclined plane to get us up to a new elevation, and we have two forces acting on some sort of a mass usually, and this mass is we're trying to transport a lot of times from the bottom to the top of the ramp or whatever, and we have normal force and gravitational force. We can use a coordinate system like this, or we can tilt it to track the motion better, so we only need one coordinate to look at the motion. We can say, okay, well, how many forces are along those coordinate systems? Well, we got normal force, we don't have to break that up, but in this case we do want to break up gravity, so a lot of times we break up gravity into mg sine theta and mg cosine theta to look at the component of gravity pulling things down the ramp and then pulling things into the ramp. And then we recognize that those are usually equal because you're not going through the ramp or floating into the air, so there's no net force in that y direction here. And then we say, okay, well, the net force basically is negative mg sine theta in the x direction in this simple case, which is ignoring friction and other forces. So when we look at a situation like this, for our problem, finally, we have a mass which is being transported from the bottom to the top of a ramp, and it gains a height of 3 meters, and the length that it traveled with the hypotenuse is going to be 5 meters, and we have a mass of 10 kilograms initially, and at finally it is at rest. So it says initially stationary and finally it stops, so it's starting at rest and it's finishing at rest. So that'll be an interesting thing to look at. And so part 1 and part 2, we want to know how much work is done by the gravitational force and how much work is done by the tension force. We could also look at how much work is done by the normal force as well. We'll see that here in a second. But what principle are we going to use? We're going to use the energy principle. We're going to assume that the ramp is very smooth. There's no friction. We're going to assume that there's no drag force. We're going to assume that the mass remains constant. We'll assume that we're much, much less than the speed of light. We don't have to do relativistic stuff. We're going to say, okay, the crate is our system, and then tension and gravity and the normal force are basically our main 3 forces from the environment that we have to consider here. And so one of the reasons why they don't ask for the work done by the normal force is, if you notice, from our formula that we used before, there's a cosine of the angle between there, and so notice how the displacement is up the ramp, and the normal force is always going to be 90 degrees to that, and cosine of 90 is 0, and so there actually is no work being done by that normal force acting up the ramp. So maybe that's why they don't ask for that, but they could have. And notice how the tension is acting in the direction of motion, and gravity is not quite acting in the direction of motion. And so not all of gravity is going to be doing work. Okay, so let's solve this problem here. So how much work is done on the crate by the gravitational force? Right, so what do we do here? So let's look at the gravitational force, and we recognize that there is some angle here between the force and the displacement. That angle is going to be 90 plus theta. And so we know that we can use this work done by a force formula to basically be, and it's a constant force, so we can use basically just force times the distance times the cosine of the angle between them. And so we can look at the angle if we wanted to. There's a couple ways to get this. Okay, so we could look at the angle and we could say, okay, well, this is a 3, 4, 5 triangle basically. So 5 is the hypotenuse, 3 is the height here, and then it would be 4 here, but we can do sine -1 or basically arc sine or whatever arc function you want to use to get theta. Basically, we can find that theta is 36.8698976, whatever, so we can round that at some point, but the basic idea is that that angle can be solved for based on the information that they gave us. And so one thing we could do then is say, okay, well, the work done by the force of gravity is, well, let's look at the force of gravity, the whole force of gravity, right? So that's going to be mg, the displacement, which is L, and then the cosine of the angle between those two, right? So the L is up the ramp, and then the force is down here, so that's going to be 90 plus theta. So we got to do cosine of 90 plus 36.87, and so you're going to get pretty much negative 300 joules. And so you can think about this as it kind of makes sense because gravity is like hurting the motion, right? So it's not really helping you, so it's doing negative work on the way up. The other way to calculate it is by looking at only the component of the force of gravity that's actually doing the work, and so that's only coming from this x component down the ramp here. And remember, we're looking at our tilted axis, which makes it a little bit maybe more tricky to think about in certain aspects. But the only component of the gravity that's doing work is the component that's counteracting the motion. Okay, the component of gravity which is into the ramp doesn't matter really. Remember, it's 90 degrees to the motion there. And so what we can say then is that mg sine theta, right, down the ramp, mg sine theta is the magnitude of my force times L, and then times the cosine of the angle between them, which in that case would be 180. And so cosine of 180 is just going to give you the negative sign, and then you got the sine of the 36.87 angle, and when you do that, you again get negative 300. The other way to think about it is basically that the work done by gravity is the negative of the change in potential energy. So we do have a change in potential energy here. So we're going from, let's just say, 0 gravitational potential, if this is our reference point, up to a new height. And so we're higher than we were, therefore we have more gravitational potential energy. And so we can say, okay, well, it's just basically equal to negative mg delta y. And so when you do negative, mg delta y, which is just 3 meters up, then again you get negative 300 joules. So whatever way you want to think about it, you're going to get negative 300 joules in terms of the work done by the gravitational force. The work done by the normal force is 0, and then the work done by tension, well, here, remember we had a little bit of acceleration and deceleration happening. We must have, right, because we started at rest and we finished at rest. So and they didn't really give us a way to easily solve for the force of tension or give us information about the force of tension. So instead of thinking about this in terms of forces, what we're going to do is think about this in terms of energy and overall energy. And so we'll think about this and say, okay, well, there's no internal work done for internal forces of the system. Remember, our system is basically the crate, so there's no forces within the crate that we need to consider. And so really the work that we need to consider for the network is going to be the work done by the surroundings, and that is the network, which is the change in kinetic energy. But wait a second, we know that the change in kinetic energy is 0 because it's starting and finishing at rest. And so, okay, well, let's break that down further. The other thing we know is that if there's going to be any changes in energy to the system, it's only coming from the work done by the surroundings, which we just said is 0. So there is no change in energy of the system. Okay, well, let's look at the work done by the surroundings. Well, what is the surroundings? It's going to be the work done by gravity plus the work done by tension, right? So those are the two main things in the surroundings that are doing work. And that's got to be equal to 0, right? Because we said the work done by the surroundings is 0. What that basically is saying is that the tension has got to be equal to the negative of gravity in terms of the work done by tension equals the negative of the work done by gravity. So when you plug that in, you just get a positive 300. What this means is that overall there was no change in energy, which means that the force of gravity was subtracting 300 joules. It was opposing the motion, whereas the force of tension was adding 300 joules, which was helping the motion. And overall, it's equal to 0. So the net work is 0 after all, which is an interesting result here. And so hopefully this problem illustrates how you can use not only the force formula for work, but also think about work in terms of the work kinetic energy theorem. And we can also think about how different forces can be doing different amounts of work, and when they add together, they could be zero. And it all comes down to that net work on the system. And so hopefully, again, this problem illustrates the energy principle, and we will see you in the next one.